To the naked eye, the tapestry seems complete. If you were to stand on a high plateau in the Atacama Desert or the desolate reaches of the outback, far from the light pollution of modern cities, the sky would appear not as a void, but as a ceiling of intricate, glowing structure. You would see the great, cloudy arch of the Milky Way slicing across the zenith, a river of diamond dust so thick that it appears to be a solid physical barrier. You would see thousands of individual stars burning with such intensity that the darkness between them feels merely like the background canvas of a painting, necessary only to provide contrast, but holding no weight of its own. In this view, the universe feels crowded, it feels busy, it feels occupied. This sensation of fullness is perhaps the most convincing illusion in the history of human observation. It is a trick of perspective, a biological filter that prioritizes the loud over the quiet, the bright over the dark, and the present over the absent. We are standing inside a crowded room, mistaking the crush of people around us for the state of the entire world. But this crowded room is an anomaly. The brightness is an exception. The reality of the cosmos is not the star. The reality is the silence that surrounds it. To understand the true architecture of the universe, we must first unlearn the lesson our eyes have taught us since birth, that the universe is defined by its lights. For most of human history, astronomy was the study of things. We catalogued the positions of the wandering planets. We named the fixed stars. We charted the sudden, terrifying appearances of comets. Our maps were maps of presence. We assumed, quite naturally, that the darkness was simply space, a neutral container, a stage upon which the celestial drama unfolded. Even as our understanding of physics matured, this bias remained. When Isaac Newton formulated the laws of gravity, he envisioned a universe that was static and infinite, where stars were scattered somewhat evenly through the dark, like seeds sown in a furrowed field. If they were not effectively uniform, he reasoned, gravity would cause them to collapse into a single massive lump. Therefore, the universe had to be balanced. It had to be full. This idea, refined over centuries, eventually crystallized into what cosmologists call the cosmological principle. In its simplest terms, this principle suggests that on large scales, the universe is homogeneous and isotropic. It means that no matter where you stand, and no matter which direction you look, the universe should look roughly the same. It implies a grand, cosmic smoothness, a consistency of texture like milk or water, and purely mathematically, on the very largest scales of the observable horizon, this holds true. But when we zoom in, even slightly from that universal scale, to the scalar superclusters and galactic neighborhoods, that smoothness shatters completely. The universe is not like milk. It is not a smooth, consistent fluid. It is a twisted, fractured, chaotic web of extreme contrasts. It is a landscape defined by jagged peaks of immense density and terrifying valleys of absolute nothingness. Consider the air in the room where you sit. It is invisible, but it is substantial. It surrounds you with a uniform pressure. You do not worry that stepping 2 feet to the left will lead you into a vacuum where you cannot breathe. The atmosphere is homogeneous. The molecules of nitrogen and oxygen are spread out with comforting equality. Now, imagine if the air behaved like the matter in our universe. In this hypothetical room, all the air molecules would not be floating freely. Instead, they would be compressed into a single, microscopic grain of sand hovering in the corner, leaving the rest of the room a perfect, suffocating vacuum. This is the scale of the discrepancy we are dealing with. Matter is not a mist. It is a sediment. When we look up at the night sky, we are seeing the sediment. We are seeing the rare, huddled clumps of baryons that have managed to cling together against the expanding dark. We see the lights of the Milky Way because we are inside the Milky Way. We are part of the clump. We are akin to a deep-sea fish living in a coral reef, assuming the entire ocean is made of coral, unaware of the thousands of miles of crushing, empty blue water that separates our reef from the next. This realization forces a profound shift in how we must visualize space. We must stop thinking of the universe as a collection of objects and start thinking of it as a collection of distances. The primary feature of the universe is not the galaxy. It is the distance between galaxies. And that distance is not merely a gap. It is a structure. In the early 20th century, as telescopes grew larger and our gaze reached deeper, we began to see past the local curtain of our own galaxy. We realized that the Milky Way was just one island universe among many. But even then, The assumption persisted that these islands were scattered somewhat randomly, floating in the cosmic sea like drift nets. We imagined a random distribution, a chaotic spray of galaxies filling the volume of space. But gravity does not allow for randomness. Gravity is an architect. It is a force of segregation. Over billions of years, gravity has been quietly, relentlessly, working to destroy the uniformity of the early universe. It amplifies differences. If a region of space has slightly more matter, gravity pulls more matter toward it, stealing from the regions that have less. It is a cosmic compounding effect, a mechanism that makes the rich richer and the poor poorer. The dense regions grow denser, lighting up with star formation and galactic collisions, becoming the neon cities of the cosmos. But what happens to the regions that are left behind? What happens to the spaces that are drained of their matter to feed the clusters? They do not merely stay empty. They evolve into vast, expansive deserts. They become the voids. These are not passive gaps. They are the result of a physical process, the grand evacuation of reality from one sector to another. By focusing on the bright lights of the clusters, we miss the vast excavation projects that made them possible. The silence between the stars is not a lack of data. It is the evidence of gravity's labor. As we stand on the precipice of this journey, we must prepare to navigate a map that is inverted. Usually, a map highlights the land masses, the continents, the islands, the cities. The oceans are merely the blue space between them. But in the cartography of the cosmos, the ratio is skewed so heavily that the landmasses are almost irrelevant. If we were to be honest about the structure of our reality, our maps would be almost entirely black, with only the faintest, thinnest, gossamer threads of light weaving through the darkness. The architecture of silence is the study of this negative space. It is the recognition that the voids are not the exception. They are the rule. They are the dominant environments of the universe. To ignore them is to ignore the ocean in favor of the driftwood. The structure of the universe is not defined by where the matter is. It is defined by where the matter is not. We are about to leave the comforting glow of the campfire. We are about to turn our backs on the high-density comfort of the Milky Way and step out into the true wilderness. It is a place where the human concept of isolation is tested against a physical reality so sparse that atoms themselves become lonely wanderers. Here, in the shadow of the galaxies, we find the first whispers of the void, a silence so profound that it does not just lack sound, it lacks the very medium for existence. This silence is not merely a lack of noise, it is a lack of events. In a frantic, overheated environment of a galaxy, the universe is a place of constant collision and transformation. Stars are born in violent collapses of gas. They live by burning their own mass. They die in supernova, that seed the vacuum with heavy elements. It is a cycle of churn and creation, a noisy, industrial process of stellar mechanics. But out in the deep fields, away from the gravitational wells of the clusters, the universe slows down to a near halt. The clock of the cosmos ticks at a different rate in the void. There are no collisions, there are no births, there is only the expansion, stretching the silence thinner and thinner across the eons. To truly grasp the architecture of this silence, we must abandon the linear way we measure our lives. We measure distance by the time it takes to travel, hours to the next city, months to the next planet, years to the next star. But the voids require a measurement of isolation. If you were floating in the center of a typical cosmic void, you would not just be far from home, you would be effectively removed from the causal narrative of the universe. The light from the nearest galaxy might take hundreds of millions of years to reach your eyes. You would be looking at history so ancient that the civilizations that live there would have risen and fallen before their image even crossed the threshold of your solitude. You would be suspended in a moment that has no relation to the rest of the physical world. This is the underdensity. It is a sterile term for a haunting reality. Cosmologists define these regions mathematically. They are areas where the density of matter drops to less than 10% of the cosmic average. But numbers fail to capture the visceral nature of such a place. It is a vacuum within a vacuum. If the space between stars in a galaxy is like the air in a thin atmosphere, the space inside a void is like the hardest vacuum ever created in a terrestrial lab, expanded to the size of 100 million light. It is the closest nature ever comes to absolute nothingness. Yet this nothingness is the scaffolding of everything. We often make the mistake of thinking that the galaxies are the structure and the voids are the gaps. But structurally, it is the reverse. The voids are the bubbles. The galaxies are merely the water draining off their surfaces. If you look at a sponge, you do not say the structure is the holes. You say the structure is the material. But in the cosmos, the holes are the dominant physical feature. They occupy the vast majority of the volume of the observable universe. They are the titanic, expanding caverns that dictate the shape of the galaxy walls. To study the universe by looking only at galaxies is like trying to understand the shape of a cavern by looking only at the moss growing on the damp walls, while ignoring the cavern itself. This inversion of perspective is difficult to accept because it diminishes us. We identify with matter. We are made of matter. We live on matter. We eat and breathe matter. We possess a baryonic bias, a prejudice in favor of protons, neutrons, and electrons. We assume that because we exist within a dense knot of material, density must be the norm. We treat the void as an anomaly, an error in the distribution, a missing piece, but the void is not missing anything. It is exactly what it is supposed to be, the primary state of the cosmos. Matter is the anomaly. Matter is the rare impurity in a solution of empty space. When we visualize the cosmic web, that grand computer-generated simulation of the universe's structure, we see a glowing lattice of purple and gold filaments, weaving together like neurons in a brain. It is beautiful, and it satisfies our desire for connection. But we must remember that those visualizations are brightened for our benefit. If we were to view the cosmic web with the naked eye, it would not be a glowing network. It would be pitch black. The filaments of galaxies would be so faint, so thin, and so hopelessly distant from one another that the web would be invisible. The reality of the web is not the strands. The reality is the gaps between the strands. The architecture of the universe, then, is an architecture of exile. The matter that makes up our world, our sun, and our bodies has been exiled from the voids. We have been pushed into the corners, swept into the gutters of gravity, and compressed into the thin, fragile sheets that separate the great expanses of nothing. We are huddled together for warmth in a cold room. The gravity that binds our galaxy together is a fortress wall, erected to keep the expansion of the void at bay. This reveals a fundamental truth about the nature of our observation. We are biased observers not just because of our biology, but because of our location. We are analyzing the ocean from the vantage point of an island. Every instrument we build, every telescope we launch, is deployed from within a region of extreme overdensity. We are trying to measure the average density of the universe from a place that is millions of times denser than the average. It is akin to trying to understand the sociology of a desert by interviewing the residents of an oasis. Our view is inherently skewed by the very conditions that allow us to exist. As we peel back the layers of light to reveal the darkness underneath, we begin to see that the universe is not a cohesive unit. It is a duality. There is the universe of light, the rare, frantic, hot universe of stars and gas, and there is the universe of the void, the cold, silent, expanding majority. For the entirety of human history, we have only known the former. We have charted the archipelagos of light and assumed they were the world. But the water is deep, and it is rising. The realization that the void dominates the physical volume of reality brings us to the edge of our own understanding. It challenges the tools we use to make sense of the world. We are creatures of object permanence. We understand things that can be touched, weighed, and seen. We have no sensory organ for the absence of things. We have no language for a scale of emptiness that renders the speed of light sluggish. We are trying to map the abyss with tools designed for the playground. This is where the physical challenge becomes a cognitive one. It is one thing to accept the mathematical fact that the universe is mostly empty space. It is another thing entirely to internalize what that means for our place in existence. It means that we are the exception. It means that the default state of the universe is not life, nor light, nor matter, but a profound, unending isolation. As we prepare to leave the safety of the architecture of silence and venture deeper into the specific nature of these voids, we must first confront the limitations of the mind that seeks to explore them. We must ask ourselves why the concept of nothing is so difficult for the human brain to process, and how our inability to comprehend the scale of the void has blinded us to its true depth for so long. The human brain is a catalogue of presence. From the moment we open our eyes as infants, Our neural pathways are forged by the processing of things. We learn to recognize faces, to grasp toys, to navigate the geometry of rooms, and to identify the source of sounds. Our entire cognitive architecture is built upon the foundation of substance. We are wired to interact with matter, to manipulate it, and to move through it. To the human mind, reality is defined by what is there. When we close our eyes and imagine a space, we inevitably populate it. We imagine walls, or a floor, or a horizon. Even when we try to imagine nothing, we usually conjure a dark canvas, a black background that still possesses the quality of a surface. We treat nothingness as a thing that can be looked at, a substance that happens to be black. This biological predisposition creates a profound barrier when we attempt to understand the cosmos. We are trying to run a simulation of the universe on hardware that evolved to hunt and gather on the African savanna. In that ancestral environment, emptiness did not exist. A clearing in the forest was not a void. It was filled with air, with scents, with the hum of insects, and the heat of the sun. The concept of a true vacuum region, devoid of matter and life, was not just irrelevant to our survival. It was impossible to encounter. Consequently, we possess no intuitive framework for it. We have no sensory memory of the void to draw upon. When astronomers speak of a region spanning 300 million light-years that contains effectively nothing, the brain rejects the scale of the isolation. It tries to fill the gap. It projects phantom structures, hypothetical ethers, or imaginary boundaries, simply to keep the terrifying reality of the infinite abyss at bay. This cognitive dissonance begins with our misunderstanding of the word empty. On Earth, when we say a cup is empty, we mean it contains no liquid, but it is full of air, it is full of microscopic dust, it is full of photons bouncing off the ceramic walls, it is a bustling metropolis of atomic activity. Even if we use advanced machinery to pump the air out of a bell jar to create a laboratory vacuum, we are merely reducing the pressure. We are creating a low-density environment within a hidden city world. We are still surrounded by the gravitational pull of the Earth, the magnetic field of the planet, and the thermal radiation of the room. We have never, not once in the history of our species, experienced a true lack of medium. The cosmological void is a different beast, entirely. It is not merely a container with the contents removed. It is a fundamental alteration of the rules of locality. In the deep voids, the concept of here begins to lose its meaning because there is no there. To contrast it with, if you were to be transported to the center of the Boötes Void, you would not feel as though you were in a dark room. You would feel as though you had been erased. Without a reference point, without a star to fix your gaze upon or a horizon to ground your equilibrium, the human mind begins to fray. Astronauts in sensory deprivation tanks report hallucinations after only a few hours. The brain, starved of input, begins to manufacture its own reality. It creates phantom lights and sounds because it cannot accept the silence. Now, project that panic onto a scale that defies mathematics. That this inability to process the void has historically shaped our scientific models. For centuries, the greatest minds in humanity struggled with the concept of action at a distance. How could the sun pull the earth if there was nothing between them to transmit the force? It seemed absurd, almost magical, that gravity could reach across a vacuum. To solve this, scientists invented the luminiferous ether. They hypothesized that the universe was filled with an invisible, weightless fluid that permeated every corner of space. They needed this fluid to exist because they needed the universe to be tactile. They needed a medium for light to wave through, just as sound waves through air. The ether was a psychological crutch, a way to make the vastness of space feel like a familiar ocean. He wanted the universe to be connected, to be touching itself, to be whole. It took the genius of Einstein and the rigorous dismantling of the ether theory to finally force humanity to face the cold truth. There is no fluid, there is no connecting medium. Gravity and light travel through the geometry of space-time itself, often traversing regions of absolute, crushing desolation. The horror vacui, the philosophical idea that nature abhors a vacuum, was proven wrong. Nature does not abhor a vacuum. Nature is composed of it. His vacuum is the canvas, and we are merely the rare specks of paint that have convinced ourselves. We are the art. The difficulty in visualizing this scales up with the size of the void. We can comfortably visualize the distance between the Earth and the Moon. We can see the Moon. It is a tangible object in our sky. we can retain a tenuous grasp on the distance to the Sun. But when we start speaking of the distance between galaxies, our mental visualization breaks down. We rely on analogies. We say, if the Milky Way were the size of a dinner plate, the nearest galaxy would be ... But the analogy fails because the human mind still places those dinner plates on a table. We imagine them sitting on a surface. We cannot mentally simulate the suspension of the plate in a void that extends infinitely in all directions. This is the cognitive horizon, the edge of our ability to conceptualize reality. Just as there is an event horizon around a black hole, beyond which we cannot see, there is a cognitive horizon in cosmology, beyond which we cannot feel. We can do the math. We can write the numbers 300 million light-years on a chalkboard. We can calculate the density of atoms per cubic meter, but we cannot feel it. We cannot truly comprehend the loneliness of a single proton drifting for 1 billion years without ever encountering another particle. This limitation is not a failure of intelligence. It is a feature of our evolution. We are social creatures, evolved for interaction. We find safety in numbers and comfort in enclosed spaces. The void is the antithesis of everything that makes us human. It is antisocial, anti-enclosure, and it is the ultimate expression of indifference. When we look at the dark patches in the sky, we are not just looking at empty space. We are looking at a hostility so passive that it does not even need to act to destroy us. It simply is, and that passive existence, that sheer, uncaring vastness triggers a primal anxiety that sits deep in the lizard brain. It is the fear of being lost, magnified to the scale of the absolute. Because of this fear, and this cognitive ceiling, we spent decades ignoring the voids. In the early days of extragalactic astronomy, when we began to map the positions of galaxies, we assumed that any gaps in the map were simply gaps in our data. If we saw a dark patch, we assumed there was dust blocking the light, or that our telescopes weren't sensitive enough to pick up the faint galaxies hiding there. We assumed the universe was smooth because we wanted it to be smooth. We wanted a universe that made sense to a brain evolved for the forest. We projected our need for density onto the canvas of the cosmos, assuming that the darkness was just light waiting to be found. We were not ready to accept that the darkness was the structure itself. We were like early mapmakers who filled the unknown oceans with sea monsters and phantom islands. Because a blank map was too terrifying to contemplate, to understand the silence of the modern universe, we must go back to a time when silence was impossible. We must rewind the cosmic clock, past the era of the galaxies, past the first stars, and back into the sweltering, opaque infancy of existence. In its earliest moments, the universe was not a collection of islands and oceans. It was a single, suffocating sea. It was a soup of unimaginable density, a blindingly bright plasma where matter and energy were locked in a frantic embrace. There were no voids, there were no gaps. If you could have existed in that primordial epoch, you would have found no direction to look, for every sightline would have ended instantly in a wall of glowing fog. It was a universe of absolute fullness, a state of perfect crushing uniformity. This uniformity was, for a fleeting moment, the defining characteristic of reality. The matter that would one day make up the Milky Way, the Andromeda Galaxy, and the distant quasars were spread out with near-perfect equality. It was a smooth, featureless canvas. But nature, in its fundamental mechanics, despises perfection. A perfectly smooth universe would have been a doomed universe. If the distribution of matter had remained exactly equal, if every cubic meter contained precisely the same amount of energy as every other cubic meter, history would have ended before it began. In a perfectly balanced universe, gravity is neutralized. Every atom is pulled equally in every direction by its neighbors, resulting in a stalemate. The cosmos would have remained a static, hot soup, expanding forever, thinning out into a cold, featureless gray mist, never forming a star, never forming a planet, and certainly never opening the vast, cavernous hollows we see today. The reason we exist, and the reason the void exists, is due to a flaw, a beautiful, necessary flaw. In the first fraction of a second, amidst the violent expansion, microscopic tremors rippled through the fabric of the cosmos. These were quantum fluctuations, teeny, random jitters in the density of the energy field. They were infinitesimally small, mere ghosts of potentiality, but they broke the symmetry. They ensured that some regions of the primordial soup were slightly but a fraction of a percent denser than others, and some regions were slightly less dense. This microscopic inequality was the seed of the void. It was the invitation that gravity was waiting for. Gravity is often described as a force of attraction, but in the context of cosmic structure, it is better understood as an amplifier. It is a mechanism that takes small differences and makes them absolute. It is greedy. When the universe began to cool and the fog cleared, gravity went to work on those tiny overdense. A region that had just a few more atoms than its neighbor began to exert a slightly stronger pull. It reached out and dragged nearby matter toward itself. As it collected more material, its mass increased, which increased its gravitational pull, which allowed it to steal even more matter from further away. It was a runaway cascade of accumulation, a snowball effect playing out on the scale of billions of light years. But we must remember the conservation of material. Gravity cannot create matter, it can only move it. If a developing prototype of galaxies is pulling gas in, it must be pulling it from somewhere. It is gathering the resources of the cosmos into a stockpile. This act of gathering inevitably necessitates an act of emptying. This is the birth of the void. The void is not a passive hole that was simply left alone. It is an excavated construction. It is the result of a cosmic theft. As the seeds of the galaxy clusters grew heavier and more influential, they began to drain their surroundings, siphoned the gas and dust from the regions of lower density, pulling the material across vast distances to feed the growing fires of structure formation. The regions that started with slightly less matter were stripped of what little they had. They were the losers in the greatest tug-of-war in history. Imagine a sheet of elastic rubber stretched tight, covered in scattered steel ball bearings. If the bearings are evenly spaced, the sheet remains flat. But if 2 or 3 bearings roll together, their combined weight creates a depression, a valley in the rubber. That valley causes other nearby bearings to roll in, deepening the depression further. But look at the space between the valleys. As the rubber stretches down into the wells of gravity, the space between them rises and thins out. It becomes a ridge, a plateau of tension. In the cosmos, this dynamic creates a texture that is difficult to visualize because it is three-dimensional. It is not just valleys and ridges. It is a volumetric emptying dot. Over the first few billion years, this process transformed the universe from a fog into a foam. This is the most accurate analogy we have for the large-scale structure of reality, the cosmic foam. Think of the head on a glass of beer or soapy water in a sink. In a foam, the liquid is not the main feature. The bubbles are. The liquid is confined to the thin films that separate the bubbles and the junctions where those films meet. The volume of the foam is almost entirely gas-empty space. The structure is maintained by the surface tension of the liquid, holding the bubbles in check. In the universe, gravity provides the tension. The galaxies and the dark matter are the liquid, flowing along the thin, fragile walls of the bubbles. The voids are the air trapped inside. His transition from a smooth sea to a bubbling foam was slow and relentless. It was a silent migration of matter on a scale that defies comprehension. Trillions of solar masses of gas flowed out of the underdense regions, abandoning them to the dark. They flowed along invisible rivers, guided by the gravitational gradients, converging onto the filaments that would become the. This creates a profound realization. The voids are not merely empty. They are empty. They are dynamic. In the early universe, the difference in density between a void and a cluster was smaller ripple in a pond. Today, the contrast is stark. The clusters have become islands of extreme density, shining with the light of trillions of stars, while the voids have become abysses where the density drops to near zero, and the process is not finished. Gravity is still working. The clusters are still pulling. The filaments are still draining the voids, tightening the noose around the emptiness, stretching the bubbles larger and thinner. You're witnessing a universe that is separating into 2 distinct phases. It is a process of distillation. The matter is condensing into smaller and tighter knots, leaving behind wider and deeper expanses of desolation. This is the skeleton of the universe. If you were to strip away the stars and look only at the gravitational potencies, you would see a vast, interconnected network of bones, the filaments surrounding the grand, spherical organs of the void. The skeleton defines the shape, but the voids define the volume. And there is another player in this game, a force that works in opposition to gravity, complicating the architecture even further. While gravity is trying to pull matter together, the expansion of the universe is trying to tear it apart. This is the cosmic tension, the balance of power that dictates the size of the foam. In the dense regions, gravity wins. It overpowers the expansion, holding the galaxies together in a tight embrace. But in the voids, there is too little matter to generate enough gravity to fight back. In the history of exploration, the matemic task has always been defined by the visible. To map a coastline, one must see the crashing waves meeting the land. To map a mountain range, one must measure the peaks that rise against the sky. We chart the physical presence of rock, water, and ice, but the cosmologist faces a challenge that no terrestrial cartographer has ever encountered: the task of mapping a shadow. The cosmic voids, by their very definition, are the absence of features. They emit no light, they reflect no solar glory, they cast no obvious silhouette against a background. They are invisible in the truest sense of the word. To find them, we cannot look for them directly. We must instead look for the walls that confine them. We must map the prison to define the cell. This requires a fundamental reimagining of what it means to see the universe. For thousands of years, astronomy was a two-dimensional science. When we look up, we are trapped inside the celestial sphere, a visual illusion that presents the cosmos as a flattened dome painted with points of light. Our eyes, and even our most powerful conventional telescopes, lacked depth perception. A faint star located just a few light-years away can appear identical to a massive galaxy, burning billions of light-years in the distance. On this flattened canvas, objects that are separated by oceans of time and space appear to be neighbors, overlapping one another in a chaotic, crowded mosaic. In this two-dimensional view, the voids are completely hidden. They are masked by the foreground stars and the background galaxies, buried behind the curtain of the local light dot to find the silence between the stars. Astronomers had to invent a way to perceive the third dimension. They had to find a method to pierce the flat canvas and measure the depth of the room. The key to this breakthrough lay not in the brightness of the light, but in the quality of the light itself. It required a shift from photography, which captures an image, to spectroscopy, which captures a fingerprint. The tool that allowed humanity to finally perceive the abyss is known as redshift. It is a concept rooted in the expansion of the universe itself. As light travels through the cosmos, it is forced to swim against the current of expanding space. The fabric of reality stretches as the light moves across it, and this stretching affects the light wave, pulling it apart, lengthening it, and shifting its color toward the red end of the spectrum. This creates a cosmic correlation. The farther away a galaxy is, the longer its light has been traveling, and the more it has been stretched. By measuring precisely how much the light has shifted, by reading the redshift, astronomers can calculate exactly how far away an object sits in the deep dark. This technique transforms a telescope from a camera into a surveyor's transit. It allows us to assign a coordinate of depth to every speck of light in the sky. It is the difference between looking at a painting of a crowd and walking through the crowd itself. Suddenly, the flat tapestry of the night sky pops open into a vast three-dimensional volume. We can separate the foreground from the background. We can push the nearby stars aside and see the deep structure that lies behind them. But knowing the distance to a single galaxy tells us very little about the shape of the nothingness. To reveal the voids, scientists had to undertake one of the most tedious and ambitious projects in the history of science, the redshift survey. Imagine trying to map the interior of a pitch-black cathedral using only a laser pointer. You cannot see the walls or the ceiling. You can only point your laser at a specific spot, measure the reflection to see how far away it is, and then mark that single data point on a graph. To understand the shape of the cathedral, you have to do this thousands, perhaps millions of times. You have to sweep the laser across every inch of the darkness, building the image dot by dot. In the late 20th century, this is exactly what astronomers began to do. They stopped looking at the sky as a picture and started scanning it as a volume. They selected thin strips of the sky, narrow wedges of the heavens, and methodically measured the redshifts of every single galaxy they could find within that strip. It was a slow, painstaking accumulation of data. Night after night, the telescopes captured the faint spectra of distant galaxies, breaking their light into rainbows, searching for the telltale shift of their spectral lines. This process is remarkably similar to a medical CT scan. A CT scanner does not photograph the human body all at once. It takes thin, cross-sectional slices. It fires X-rays through a narrow plane of the body, creating a 2D image of that specific slice. By stacking these slices together, doctors can reconstruct the 3D geometry of the organs and bones. Cosmologists adopted the same strategy. They began to slice the sky dot. As the data from these slices began to accumulate, the computers plotted the position of each galaxy as a single point in a three-dimensional graph. At first, the points seemed random, a scattershot of noise. But as the sample size grew from hundreds of galaxies to thousands, a pattern began to emerge from the static. The points were not distributed evenly like dust in a room. They were lining up. This was the moment the invisible became visible. The computer screens did not show a uniform haze of galaxy points. Instead, they revealed a negative image. The galaxies were clustering together in long, thin chains and dense knots. But more importantly, there were vast regions on the graph where there were no points at all. The data revealed huge, circular vacancies, gaping holes in the map where the survey beam had traveled for millions of light years without hitting anything significant. These were the first maps of the voids. They appeared on the monitors like bubbles in a block of ice, defined entirely by the impurities trapped in the frozen water. The galaxies were merely the boundary markers. By connecting the dots of the light, the astronomers traced the outline of the dark. They realized that two-way a shadow. You do not measure the shadow itself. You measure the curvature of the light that bends around it. You measure the recessional velocity of the galaxies on the near side and the far side, determining exactly where the matter stops and the emptiness begins. This transition to three-dimensional cosmography changed everything. It revealed that the universe was not a collection of isolated objects, but a continuous landscape. Just as a topographical map reveals the logic of a watershed, showing how water flows from the peaks to the valleys, these 3D maps revealed the gravitational logic of the cosmos. We could see the walls of galaxies, thin membranes of light that acted as the partitions between the voids. We could see the filaments, the bridges of matter connecting the clusters, and dominating the entire view were the great, spherical absences. The psychological impact of these early maps cannot be overstated. Before the redshift surveys, the voids were theoretical, hypothetical consequences of gravity that might or might not exist. But once the data was plotted, the voids became undeniable architectural features. They were the rooms in which the galaxies lived. The maps showed us that we had been studying the paint on the walls while ignoring the size of the room. We had been obsessed with the furniture of the universe, the stars and planets, while failing to perceive the house itself. The early surveys, such as the CFA Redshift survey, produced images that have become iconic in the field of cosmology. One famous slice, often called the stickman, because the arrangement of galaxy clusters resembled a stick figure, showed a massive figure standing in a cavernous loop of empty space. This was a direct visualization of the bubble-like nature of reality. It was a slice through the cosmic foam. It proved that the distribution of matter was not random, nor was it uniform. It was cellular. But mapping these regions is not as simple as taking a snapshot. The voids are elusive. They are not perfect spheres with hard shells. They are irregular, organic shapes, with boundaries that are often diffuse and difficult to define. The galaxies that make up the walls are not touching. They are separated by their own vast distances, merely appearing as a wall when viewed from a perspective of hundreds of millions of light years. The mapmaker must decide where the void ends and the filament begins. It is an exercise in defining the point at which something becomes nothing. Science often advances through loud discoveries, the explosion of a rocket, the smashing of an atom, or the sudden flare of a supernova. But sometimes, the most profound shifts in our understanding of reality arrive not with a bang, but with a silence. In 1981, a group of 4 astronomers pointed a telescope toward a patch of sky in the constellation Boötes, the herdsmen. They were not looking for a monster. They were engaged in what was supposed to be a routine act of cartography, a statistical exercise to confirm the standard density of the cosmos. They expected to find a typical scatter of light, a mundane drift of galaxies similar to the neighborhood of our own Milky Way. Instead, they found a silence so deep and so wide that it threatened to dismantle the standard model of the universe. The year 1981 stood on the precipice of the digital revolution in astronomy. but the work was still tactile, slow, and arduous. The scientific community was still largely wedded to the idea of the smooth universe. The cosmological principle was the governing law. If you looked at a large enough volume of space, the distribution of matter should be roughly equal. There should be no special places, no grand clumping, and certainly no grand emptiness. It was a comforting, democratic view of physics. Matter was everywhere, and it was everywhere in roughly the same amount. It was in this climate that Robert Kushner, Augustus Omler Jr., Paul Schechter, and Stephen Scheckman, team later colloquially known as the Gang of Four, began their survey. Their goal was to drill a core sample into the deep universe, rather than taking a wide-angle photograph of the entire sky, which lacks depth. They chose to focus on narrow, specific cones of vision. They were effectively dropping a sounding line into the cosmic ocean, measuring the redshift of every galaxy they encountered along a specific line of sight to determine how far away it was. The technique was precise. They selected 3 small, separate fields within the boat's constellation. They aimed their instruments and began to count the galaxies, measuring their distance by the stretching of their light. As they moved outward from Earth, the data, initially, behaved as expected. They found galaxies at nearby distances. They found galaxies at middle distances. The distribution seemed normal, a reassuring tick-tock of matter, confirming the theories of the day. But as their gaze pushed deeper, past the familiar foreground of the local universe, and into the range of recessional velocities between 12,000 and 18,000 kilometers per second, the data suddenly stopped. The steady rhythm of galaxies vanished. At first, it appeared to be a statistical fluke. In a random universe, you expect gaps. You expect small pockets of low density, just as you expect pauses in a conversation or clearings in a forest. But as the redshift continued to climb, representing millions upon millions of light-years of travel, the silence did not break. The data feed remained obstinately blank. There were no spikes of light. There were no clusters. There were no stray spirals. The sounding line kept dropping, mile after cosmic mile, and it was hitting nothing but the bottomless dark. For a distance that translates to roughly 250 million light-years, the survey found an almost total absence of matter. Then, just as abruptly as it had begun, the silence ended. At the far side of this abyss, the galaxies reappeared in the data, resuming their normal distribution as if nothing had happened. The astronomers had looked through a wall of galaxies, peered into a cavern of unimaginable size, and then seen the wall on the other side. The sheer scale of the nothingness was paralyzing. This was not a gap, it was a chasm. The region they had stumbled upon was a sphere of emptiness, approximately 330 million light-years in diameter. To put this in perspective, the distance from the Milky Way to our nearest major neighbor, Andromeda, is about 2.5 million light. This new void could fit that journey back and forth more than 100 times. It was a volume of space so vast that it could comfortably swallow 10,000 galaxies the size of the Milky Way. Yet the survey suggested it contained almost none. The immediate reaction was not celebration, but confusion. In science, when you find a result that violates the established order by such a massive margin, your first assumption is not that you have discovered a new phenomenon, but that you have made a mistake. The team questioned their equipment. They questioned their calibration. They wondered if they had simply been incredibly unlucky. Perhaps they had pointed their telescope through a thick cloud of intergalactic dust that was obscuring the galaxies behind it, creating the illusion of a void. But the physics of redshift ruled out the dust theory. If dust were blocking the light, it would obscure everything behind it. But they could see the galaxies behind the void perfectly well. The light from the far side was reaching Earth unimpeded. This meant the space in between was transparent. It was not a dark cloud hiding the stars. It was a transparent desert where stars simply did not exist. They also considered the tube, theoried the idea that they had accidentally looked down along a narrow tunnel of emptiness, like looking through a straw in a haystack. But they had sampled 3 different fields in the sky, separated by significant angles, and they had found the same emptiness in all of them. The geometry implied that these weren't separate tunnels. They were looking into different parts of a single, colossal bubble. When the team published their findings in the Astrophysical Journal in a paper titled "A Million Cubic Megaparsecs Void in Boats," the title itself carried a weight of disbelief. They were reporting a hole in the universe that constituted nearly 1% of the entire observable volume known at the time. It was an anomaly that simply should not exist. According to the theories of galaxy formation available in 1981, there hadn't been enough time since the Big Bang for gravity to clear out a space that large. Moving that much matter, clearing a volume of that magnitude, would require a gravitational shovel moving faster than the laws of physics seemed to allow. The great nothing of boats became an immediate problem. It stood as a stark, dark monument to our ignorance. It mocked the idea of the smooth universe. It suggested that our local environment, the dense star-filled region of the Virgo supercluster, was not the norm. We were living in a crowded tenement, unaware that just down the street lay a desolate, expanding wilderness. The discovery forced a reckoning with the psychological experience of the observer. Up until this moment, the void was a mathematical concept, a variable in an equation. Now, it was a place. It had a location. You could point to it on a star chart. It sits there, in the direction of the herdsman, a region of space so devoid of content that it challenges the very definition of presence. The human mind struggles to visualize a vacuum of this size. If you were to travel at the speed of light, a speed that allows you to circle the Earth 7 times in a single second, it would still take you 330 million years to cross the Boötes Void. During that entire journey, you would likely never pass within hailing distance of another star. The astronomers of 1981 had peeled back the skin of the night sky and found a hollow interior. The question was no longer, is the universe uniform? The question became, why? Is the universe empty? They had found the first true supervoid in its existence, demanded an explanation that would rewrite the history of cosmic evolution. The discovery of the Boötes Void was akin to finding a hidden room in a house. We thought we knew perfectly. It was shocking, confusing, and isolated. But as the decades passed and our vision sharpened, we came to a far more unsettling realization. The house is not made of rooms. It is made of hidden spaces. Boötes was not a freak accident of cosmic geography, nor was it a unique scar on the face of the deep. It was merely the first clear glimpse of the pattern. It was the first time we stepped back far enough to see the weave of the fabric. Whence the initial disbelief subsided, the astronomers began to look for these absences everywhere. And they found them. They found the local void, a region of desolation, bordering our own local group. They found the Boötes Void, a trench of darkness separating grand walls of galaxies. They found that the great nothing of 1981 was, in fact, a standard component of the universe's machinery. We realized that we had been describing the universe like a tourist, describing a net, by talking only about the strings, ignoring the holes that give the net its shape. The universe is not a collection of galaxies with holes in between. It is a collection of holes with galaxies threaded along the edge. But even as we adjusted to this new cellular reality, the universe had one more scale of emptiness to reveal, a scale so massive that it threatened to break the laws of physics entirely. To find it, we had to look beyond the galaxies. We had to look at the edge of the observable universe itself. We turned our instruments to the cosmic microwave background, the CMB. This is the afterglow of the Big Bang, the oldest light in existence, streaming toward us from every direction. It is a snapshot of the infant universe, taken 380,000 years after the moment of creation. When we map this light, we see a bath of heat that is almost perfectly uniform. It is a smooth, glowing wall of radiation, measuring 2.7 Kelvin. However, in 2004, satellites mapping this ancient light found a bruise in the southern hemisphere of the sky, in the direction of the constellation Eridanus. There is a massive patch of the sky that is colder than it should be. It is significantly larger than the statistical random fluctuations allowed by our theories. It is a chilly anomaly in a warm room. For years, this CMB Cold Spot was the subject of intense debate. Was it a calibration error? Was it a statistical fluke? Or was it a window into something else? The answer arrived when we correlated the temperature of the ancient light with the distribution of the foreground galaxies. The light from the cold spot was cold because it had traveled through a desert of unprecedented size. It had passed through the Eridanus Supervoid. If the Boötes Void is a cavern, the Eridanus Supervoid is an abyss that defies metaphor. It is estimated to be 1.8 billion light-years across. It is not just a lack of galaxies, it is a lack of the universe itself. It is a chasm so wide that it consumes a significant fraction of the observable horizon. When we stare into the Eridanus Supervoid, we are looking at a structure that is too big to exist under the standard models of cosmic inflation. There simply shouldn't have been enough time since the beginning of the universe for a hole this size to grow. It is a monster that has outpaced history. How does an empty space make the background light colder? The mechanism reveals the true, exhausting nature of the void. As a photon of light travels through the universe, it must navigate the hills and valleys of gravity. When light passes a massive galaxy cluster, it falls into a gravity well, gaining energy as it speeds up, much like a cyclist rolling down a hill. As it climbs out the other side, it loses that energy, slowing down again. In a static universe, the energy gained and lost would balance out perfectly, but our universe is not static. It is expanding, and in a supervoid, this expansion is brutal. Imagine a photon of light entering the Eridanus Supervoid. It is entering a vast, flat plane where gravity is incredibly weak. But as it travels across this billion light-year expanse, the universe expands, the space stretches, the exit on the other side moves further away. The hill it has to climb to get out becomes steeper and longer while the photon is still crossing the bottom. By the time the light finally climbs out of the void and reaches our telescopes, it has lost more energy than it started with. It is tired. It has been drained by the journey through the nothingness. This loss of energy manifests as a drop in temperature. The cold spot is effectively a shadow cast by a supervoid, a permanent record of light's exhaustion as it crossed the greatest desert in reality. His discovery confirmed that the voids are not just passive gaps, they are active environments that shape the energy of the cosmos. They are the supervoid complex. We now understand that these structures are the dominant volume of the universe. We live in a cosmic honeycomb. The walls of the honeycomb are the superclusters, the Sloan Great Wall, the Boötes Great Wall, the Laniakea cluster. These are the thin, fragile boundaries where life is permitted to exist. Inside the cells of the honeycomb are the voids, expanding bubbles of isolation that are slowly squeezing the life out of the walls. This cellular structure forces us to re-evaluate our movement. We tend to think of the Milky Way as a ship sailing through space, perhaps orbiting the center of our local cluster. But the dynamics of the supervoid complex suggests a more fluid, river-like motion. The galaxies are not just orbiting, they are flowing. They are being pushed and pulled by the landscape of density. And this brings us to the most unsettling realization of modern cosmography. We are running away. For decades, astronomers measured the motion of our local group of galaxies, the Milky Way, Andromeda, and our smaller satellite galaxies. We knew we were moving at a tremendous speed, roughly 630 kilometers per second, relative to the background radiation. We assumed we were being pulled toward something massive. We called it the Great Attractor, a gravitational anomaly pulling us toward the Centaurus constellation. It made sense. Gravity attracts. We are falling toward a heavy object, but math never quite worked. The Great Attractor wasn't heavy enough to account for our speed. We were moving too fast. It was as if we were falling down a hill, but the slope was steeper than the gravity of the attractor could explain. The missing piece of the puzzle was behind us. We weren't just being pulled, we were being pushed. In 2017, a team of cosmologists mapped the flows of the local universe and discovered a region of profound emptiness directly opposite the Great Attractor. They named it the Dipole Repeller. It is a void, sitting in the blind spot behind the Milky Way. It is a region of such low density that it effectively acts as a repulsive force. Now, we must be careful with our language here. A void does not have a force. It cannot push. Nothingness has no hands. A vacuum cannot exert pressure on a galaxy. So how can a void repel an entire galaxy cluster? How can the absence of a thing move a thing? The answer lies in the relative balance of the cosmos. Imagine a tug-of-war. On one side, you have the Great Attractor, a team of strong, heavy galaxies pulling the rope. On the other side, inside the Dipole Repeller, you have no one. You have an empty field. The repulsion is an illusion of contrast, because there is no gravity behind us to hold us back, and plenty of gravity in front of us to pull us forward. The net result is a headlong rush away from the void. The void pushes us simply by failing to pull. If we could strip the universe of its stars and look only at the forces governing its shape, we would see a battlefield. For 13.8 billion years, the cosmos has been the stage for a silent, desperate war between two opposing titans. On one side stands gravity, the architect of connection. Gravity is the force of gathering, the pull that seeks to bring matter together, to bind atoms into stars, and stars into galaxies. It is a force of intimacy. It wants the universe to be small, dense, and huddled together. On the other side stands the expansion, the primordial momentum of the Big Bang, pushing outward, seeking to stretch the canvas of reality until it rips. It is the force of isolation. It wants the universe to be cold, empty, and alone. In the crowded clusters where we live, gravity is winning. The mass of the Milky Way, the Andromeda galaxy, and the Virgo cluster acts as an anchor. The density here is so high that space itself is held in check. Unable to stretch the distance between our stars, we are protected. We live in a gravitational fortress that keeps the expansion at bay. But out in the deep voids, the war is over. Gravity is lost. In the great hollows like Boötes and Eridanus, there is almost no matter to generate a gravitational field. There are no anchors. There is no braking mechanism. In these regions, the expansion of the universe is unbridled. It's wild. The voids are not merely passive gaps that are getting larger because the walls are moving apart. They are the active engines of the expansion itself. They are the places where space is being manufactured at the fastest rate. This realization forces us to confront the darkest mystery in modern physics. For most of the 20th century, astronomers assumed that the expansion of the universe was slowing down. They believed that the mutual gravity of all the galaxies was acting like a brake, slowly retarding the outward momentum of the Big Bang. They expected that eventually, the universe would coast to a halt, or perhaps even collapse back in on itself. But in the late 1990s, when we measured the distance to distant supernova, we found the opposite. The universe is not slowing down, it is speeding up. It is accelerating. The driver of this acceleration is an invisible, repulsive pressure that permeates the vacuum. We call it dark energy. We do not know what it is. We do not know why it exists. We only know what it does. It pushes. It is a property of space itself. Unlike matter, which dilutes as it spreads out, dark energy remains constant. If you double the amount of space, you have twice as much dark energy. This makes the voids the most dangerous places in the cosmos. Because the voids contain the vast majority of the volume of the universe, they contain the vast majority of the dark energy. They are the reservoirs of this mysterious, repulsive force. While the gravity in the galaxy clusters fights against dark energy, cancelling out its effects locally, the voids have no such defense. Inside a void, dark energy is the undisputed tyrant. It pushes the boundaries of the void outward with relentless, compounding force. Imagine a balloon inflating inside a wire mesh cage. The wire mesh represents the filaments of galaxies, the thin, fragile structures of matter. The air inside the balloon is the dark energy. As the balloon expands, it presses against the wire, stretching it, thinning it, and pushing the wires further apart. The voids are the balloons. They are inflating from the inside out, exerting a colossal pressure on the cosmic web. They are squeezing the galaxy filaments, compressing the matter into tighter and tighter walls, while simultaneously driving those walls apart from one another. This changes our perception of the cosmic web. We used to think of the filaments as the primary structure, like a spider's web hanging in a room. But the filaments are merely the boundaries between the expanding bubbles. The dynamics of the universe are driven by the bubbles. The voids are swelling. They are crowding the universe. As they grow, they collide with one another, merging into larger and larger eating away at the delicate strands of matter that separate them. We are witnessing the rise of the accelerating abyss. The voids are effectively the power plants of cosmic isolation. Every second, they generate millions of cubic light-years of new space, adding to the distance that separates the islands of life. This creation of space is silent, invisible, and unstoppable. It is not an explosion, it is a stretching. If you were floating in the center of a void, you would not feel a force pushing you. You would simply find that the distant galaxies are receding from you faster today than they were yesterday. The horizon is fleeing. This acceleration has profound implications for the future of the night sky. Because the voids are expanding faster than the speed of light allows information to travel, they are slowly erasing our connection to the rest of the cosmos. The voids are widening the gaps between the superclusters, to the point where light can no longer bridge the divide. They are creating event horizons around our local island of matter. Consider the view from a planet situated on the lonely edge of a void, looking out into the chasm. For billions of years, the observers on that world would have seen the faint glow of galaxies on the far side of the emptiness. But as the dark energy within the void accelerates the expansion, those distant galaxies will begin to fade. Their light will be stretched into invisibility, redshifted until it vanishes from the spectrum. Eventually, the expansion speed will exceed the speed of light. The photons leaving the far wall will never reach the observer. The image of the distant universe will simply detach and drift away into the dark. The void acts as a cosmic eraser. It is scrubbing the sky clean. It is dismantling the causal connections that bind the universe together. We are moving toward a future where the voids have won completely. They will continue to swell, pushing the galaxy clusters so far apart that each one would become a lonely, isolated island universe, entirely unaware of the others. The observable universe will shrink, not in size, but in content. The vast, rich tapestry of billions of galaxies will be reduced to a single, local patch of stars, surrounded by an infinite, accelerating nothingness. This dominance of the void explains why the universe looks the way it does today. The cellular structure, the foam, is the natural result of dark energy pushing matter out of the way. We are living in the late stages of a transition. The era of gravity is ending. The era of the void is beginning. The universe is transitioning from a place defined by structure to a place defined by expansion. But there is a deeper, more unsettling question hiding in the physics of this acceleration. If the voids are the source of the repulsion, and if they are growing larger, does that mean the repulsive force is growing stronger? Are we heading for a big rip, where the expansion becomes so violent that it tears apart not just the galaxy clusters, but the galaxies themselves? To answer this, we must look at the emptiness of the void with even more scrutiny. Is it truly empty? Or is the vacuum itself a seething, frothing ocean of potential energy that we have barely begun to comprehend? The standard model suggests that the energy density of the void is constant, the cosmological constant. But there are other theories. Theories that suggest the void is evolving. Theories that suggest the nothingness is hungry. In these models, the void does not just push, it consumes. As the volume of space increases, the nature of the vacuum energy might change, becoming more phantom-like, more aggressive. The phantom energy hypothesis suggests that the acceleration will not just continue, it will increase exponentially. The voids will not just separate the clusters, they will invade them. Throughout this journey, we have maintained a comfortable distance. We have spoken of the voids as out there vast, distant deserts located in the constellation of Boötes, or Eridanus, or the cold southern skies. We have positioned ourselves as the safe observers, standing on the solid ground of a dense galactic metropolis, looking out at the wilderness through the window of our telescopes. We have assumed that the Milky Way, our home, resides in a normal region of the universe, a standard, average neighborhood teeming with a typical amount of matter. We cling to the Copernican principle, the humble scientific idea that there is nothing special about our location in space. We are not the center, we are not the edge, we are just somewhere. But there is a growing whisper in the data that suggests we have been wrong about our own address. As our measurements of the cosmos have become more precise, a troubling discrepancy has emerged, a subtle crack in the foundation of our map. When we measured the expansion rate of the universe using the ancient light of the cosmic microwave background, light from the edge of reality, we get one number. But when we measure the expansion rate, using the stars and supernova in our own local neighborhood, we get a different number. The local universe appears to be expanding faster than it should. For years, this tension has frustrated astronomers, leading to wild theories about new physics or errors in the lenses. But there is a simpler, more haunting explanation. The reason the local universe looks different is that the local universe is different. We are not standing on solid ground looking out at the void. We are floating inside one dot in 2013. Astronomers Kennan, Barger, and Cowie proposed a hypothesis that reframes our entire existence. They analyzed the density of galaxies in a sphere surrounding the Milky Way and found that the numbers were consistently too low. They suggested that our galaxy, along with the Andromeda Galaxy, the Virgo cluster, and even the entirety of our local supercluster, Laniakea, is residing inside a colossally vast region of underdensity. They named it the KBC Void. If this hypothesis holds true, the scale of our isolation is staggering. The KBC Void is not a small pocket. It is estimated to be 2 billion light-years in diameter. It is 7 times larger than the Boötes Void. It is so large that it encompasses everything we have ever seen with the naked eye. Every star you can point to, every nebula, every nearby galaxy cluster, it is all trapped inside the same bubble. We are living in a universe-sized cavern, and our local supercluster is merely a thin filament of dust floating near the center of the emptiness. This realization fundamentally inverts our psychological relationship with the dark. We are not the travelers looking at the desert. We are the oasis that doesn't realize it is surrounded by sand. The reason the local universe appears to be expanding faster is gravity, or rather, the lack of it. Because we are inside a void, there is less matter around us to hold things back. But more importantly, the dense regions outside the bubble, the distant walls of the KBC Void, 2 billion light-years away, are pulling us outward. We are being siphoned away from the center of the void toward the edge. The flow of the cosmos is dragging us out of the hollow dot. Imagine living in a valley surrounded by high mountains. You might think the world consists of the valley floor. But if you realized that the rivers were flowing too fast, rushing away from you in every direction, you would understand that you are not on a flat plain, but on a peak, or inside a basin that is emptying out. We are in the basin. The KBC Void is the largest structure we have ever attempted to quantify, and we are the microscopic residents of its interior. This local bubble theory explains why the night sky deceives us. When we look up, we see this band of the Milky Way. We see a sky thick with stars. It feels crowded, but this is a local illusion. It is like standing in the middle of a brightly lit stadium at night. The lights of the stadium are blindingly intense, creating a sense of a contained, busy world. But if you were to turn off the stadium lights, you would realize you are standing in the middle of a vast, uninhabited plain, miles from the nearest city. We are blinded by our own local brightness. The density of the Milky Way and the local group masks the fact that just beyond our backyard, the density drops off a cliff. We are living in a cosmic backwater. In the grand geography of the universe, the KBC Void is a region of depletion. It is a place where the universe has exhaled. While there are other galaxies here with us, we are statistically alone compared to the rich, dense walls that lie far beyond our horizon. We are the lonely observers. The light that reaches us from the distant universe has to cross 1 billion light-years of near vacuum just to reach our telescopes. We are receiving postcards from a world that is fundamentally more crowded than our own. This context adds a layer of fragility to our existence. We often think of life as a product of abundance, plentiful water, plentiful sunlight, plentiful chemicals. But on a cosmic scale, we are the product of scarcity. We exist in a region where the destructive, chaotic forces of high-density environments are absent. Perhaps that is why we are here. In the dense walls of the superclusters, where galaxies collide and black holes merge with violent frequency, the conditions might be too volatile for long-term stability. The void, with its quiet, expanding silence, might be the only safe harbor for life. The bubble is not a prison. It is a cradle. As we stare into the black spaces between the stars, we must now recognize that the blackness is not over there. It is here. It is pressing against the heliosphere of our sun. It is the medium through which our planet moves. The void is our environment. We are creatures of the underdensity, evolved to survive in the rare, quiet corners of a universe that is mostly noise and fire, or mostly absolute cold. The journey to find the true depth of the void has brought us full circle. We started by looking for holes in the map, and we ended by realizing the map is almost entirely whole. The solid ground we thought we stood upon is a fleeting filament, a temporary gathering of atoms in an expanding ocean of nothing. The voids are not anomalies to be catalogued. They are the primary truth of the physical world. Matter is the afterthought.